Having seen an introduction to convolutional neural networks, we saw a couple of new layers that you can have in a neural network. A convolutional layer, a pooling layer. Now we ask the question, with these new layers, how does this affect backpropagation the way we saw it earlier? Before we go there, let's revisit our exercise from last class, which was given a 32 cross 32 cross 3 image and 6 filters of size 5 cross 5 cross 3. What is the dimension of the output volume with a stride of 1 and padding of 0? The answer is straightforward. W2 is equal to W1 minus F plus 2P by S plus 1. A similar formula for H2. You simply plug in the values and you get 28 cross 6, which is the depth of the output because of the number of filters. We did leave behind another question, which was, is the max pooling layer differentiable and how do you backpropagate across it? And this is something that we will visit at the end of this lecture. Let's now start and try to do backpropagation across a convolutional layer first. A large part of this lecture's content is adapted from Dhruv Batra's excellent lectures at Georgia Tech. To begin, let's assume a grayscale image. We assume that the number of input channels C is equal to 1. You should see that this won't affect the derivation per se. It just makes it simpler for explaining. Also, we're going to assume the number of convolutional filters to be 1, which means the size of your output map or the depth of your output map will also be 1. But each convolution will follow the same procedure to be able to compute its gradients. To start, let's consider a single convolutional filter. Let's assume the size of that filter to be K1 cross K2. This is applied to an image which is of size N1 cross N2, and you get an output Y which is of size M1 cross M2. Visually speaking, this is your space. You have an input X, filter W, and output Y. From definition of convolution, we know that an element of the output Y at Yj, Y at Ij, can be written as summation A going from 0 to K1 minus 1, B going from 0 to K2 minus 1, X of I minus A, J minus B into WAB. Note here that we are not placing the filter at the center of the input pixel, but at a corner. This doesn't matter. This is only to make this expression a little simpler to see. So we would make it, the rest of the derivation, a little simpler to understand. We now are given a loss function L, which is used to train a CNN. So for our convolutional layer, there are two quantities that we have to compute. One is dou L by dou W, the gradient of the loss with respect to every weight in every filter, and dou L by dou X, which is the loss with respect to every pixel of the input, because that is necessary to backpropagate further to an earlier layer. We're going to try to derive the gradient for each of these quantities using chain rule. Let's start with dou L by dou W, the gradient with respect to the weights in the filter. To do this, let's consider one particular weight in the convolutional filter. Let's say that you have W, A prime, B prime as one location on your filter. So if you have your filter to be W, which is K1 cross K2 dimensions, you have one of those values inside them to be W, A prime, B prime. We now want to compute the gradient of the loss with respect to that particular weight, and then this can be generalized to all weights in that filter. To do this, let's ask the question, if you used a filter in a convolutional layer, which is W, how many pixels and which pixels in the output or the next layer Y does that particular weight value affect? Because remember, the way backpropagation is done, all the values that a particular pixel impacts in the next layer, we have to accumulate all those gradients back into the gradient at that particular pixel. This is what we saw with feed-forward neural networks. So in this case, the question is, if we took the weight at A prime, B prime, what all pixels in the next layer's map does that particular weight affect? The answer is every pixel in Y, because every pixel in Y is obtained by a convolution of the filter with a certain location in X, while a certain pixel in Y depends only on a few pixels in X. It does depend on every value in W, which is the filter. So each pixel in the output corresponds to one position of the filter overlapping the input, and every pixel in the output is a weighted sum of a part of the input image, but the weight in the filter affects every pixel in the output. Now let's move forward. We now write dou L by dou W at A prime B prime given by summation of the entire dimension of Y. Remember, Y we said has a dimension of M1 cross M2. So we have to sum over all of these gradients, where you have dou L by dou Yj, which is going to be the gradient of the loss until one particular pixel in that next layer's map, into dou Yij by dou W A prime B prime. Chain rule. Dou L by dou Y we assume is already known through backpropagation until that particular step. Our challenge now for the convolutional layer is to compute dou Y by dou W. In particular, dou Y at Ij by dou W at A prime B prime. That's the quantity that we now have to compute this overall gradient of loss with respect to W at A prime B prime. Let's consider that particular quantity now, which is dou Y at Ij with respect to dou W at A prime B prime. By definition of convolution, once again we have Y at Ij is, this follows from the standard definition of convolution. This K1, K2 are the filter sizes, and this is your first principles definition of convolution. Using this, we can now say dou Yij by dou W A prime B prime can be written as dou Yij by dou W A prime B prime, which is, you now expand Yij in terms of the entire output that you have from the first equation. So you have the entire RHS of the first equation, you put that in there. Now in all these summations, there is only one summation, one term here that is going to depend on W A prime B prime. Remember, in one convolution, one particular filter value is convolved with only one pixel in the input in that single convolution operation. When you move the filter to the next location, it may contribute something else in the other location. But in one single convolution operation, one value in the filter is multiplied by only one input pixel. And that term now is going to be W A prime B prime into X I minus A prime J minus B prime. Every other term in this double summation, when you differentiate with respect to W A prime B prime, will become 0 because it does not depend on W A prime B prime. This quantity trivially becomes X at I minus A prime Y minus B prime. Let's see how to use this. Let's plug this back in. We now have dou L with respect to W A prime B prime equal to summation over all the pixels in Y, dou L by dou Y for every pixel in Y, into the second term which we just computed on the previous slide, which turns out to be X at I minus A prime Y minus B prime. Look carefully. This is now the convolution of x and dou L by dou y, which is beautiful. Dou L by dou y, remember, is also going to have the dimensions of y. It also, that gradient, that set of gradients will also look like an image because you have a gradient of the loss with respect to every pixel in y. So that is going to form one matrix, and X is a matrix by itself. The convolution of X and dou L by dou y is dou L by dou W at A prime, B prime. So you can compute this as a convolution in the backpropagation step. Let's now move on to the next quantity, which is dou L by dou X, which is the gradient with respect to the inputs of that layer, of that convolutional layer. Let's once again consider a single input pixel X at I prime, J prime. Let's again ask the question, which pixels in Y would be affected by this particular pixel in X? If we see it visually, we can say that given an X, and let's say there's one pixel given by this red square, which is at I prime, J prime. When it's convolved with W, you would now have this, it would affect this entire range of pixels that go from I prime by J prime to I prime plus K1 minus 1 and J prime plus K2 minus 1. Why is it like this? Why is it not centered at I prime, J prime? Because that's the way we define convolution in this context for simplicity. If we had defined convolution as going from minus K1 by 2 to plus K1 by 2, it would have been centered. But because this is the way we define convolution, the indices went from 0 to K1 minus 1 and B to K2 minus 1. You would now have these pixels here represented by this dotted square, which are the pixels that would be affected by I prime, J prime. Now we call this region P, and we now know that the gradients of the loss with respect to these pixels will be influencing the gradient of the loss with respect to this pixel. All other pixels in Y do not have a contribution from this pixel, and hence those gradients of L with respect to Y do not matter to us. Let's now say dou L by dou X at I prime, J prime is summation over all pixels in that region P, dou L by dou YP into dou YP by dou X at I prime, J prime. From the figure in the previous slide, we can now define that region P as going from 0 to K1 minus 1, B going from 0 to K2 minus 1, dou L at a particular pixel Y, I prime plus A, J prime plus B, and the derivative of Y at I prime plus A, J prime by B plus B with respect to X at I prime, J prime. Rather, if you see the previous slide, we are taking each pixel here and adding them all up and saying that we want the gradient of a particular pixel in this region P with respect to this pixel in X. That's what we are writing in this summation. The left quantity here is known because we assume that all the dou Y until dou Y's are known until that time. We are only worried about how to compute the backprop across a single convolutional layer. If there were more convolutional layers, the same procedure would be applied iteratively. But the second quantity here is currently not known to us. Dou Y of I prime plus A and J prime plus B with respect to X at I prime, J prime. Let's try to compute this on the next slide. From the definition of convolution, once again, we have Y at I prime, J prime given by this equation. This once again comes from the basic definition of convolution. So if this was the definition of Y at I prime, J prime, then the definition of Y at I prime plus A, J prime plus B, which is going to be another pixel location, will be replace wherever I prime is there by I prime plus A, replace wherever J prime is there by J prime plus B. So I prime plus A minus A becomes I prime, J prime plus B minus B becomes J prime, and WAB stays as it is. Now the derivative of I prime plus A, J prime plus B with respect to I prime, J prime will be that one single term WAB for a particular choice of A and B. For a different choice of A and B, it would be that term in the summation. As we said for the previous derivative, dou L by dou W also, all the other terms in the summation would not affect the derivative with respect to one particular AB. So this is the quantity that we have for dou Y at a particular pixel location with respect to dou X at I prime J prime. Let's now plug this back. We have dou L by dou X at I prime J prime to be, for all the pixels in the region P, dou L by dou Y at one of those pixels into WAB for this choice of A and B. Once again, this becomes interesting. This looks like the definition of cross correlation. It's the cross correlation of dou L by dou Y with W, the filter. Rather, we can say it's the convolution of the filter flipped with dou L by dou Y. We know that cross correlation and convolution differ by that flip of the filter, and that becomes by a flip by 180 degrees, which is a flip in two directions, and that's what now we have here. Dou L by dou Y into a double convolution with a double flipped filter. This is interesting again because even now the chain rule across the convolutional layer to compute dou L by dou X can be computed as a convolution. Why does this matter? Recall our discussion of image frequencies in the first week. We said that convolution can be evaluated through very efficient methods such as fast Fourier transform. You could use all that to efficiently compute these gradients during backpropagation in this step. Now we are left with one question. So that concludes how backpropagation is done across a convolutional layer. There are only two quantities, W and X. We now still are left with how do you backpropagate across a pooling layer. As we said before, a pooling layer is parameter free. It does not have any weights. There are no weights to update, no gradients. The only gradients we have to compute are the gradients with respect to X in the previous layer to allow the gradients to propagate through to earlier layers. How do we do this? If we have max pooling, let's take this visual example on the right. So you can see here that these red, green, yellow and blue regions are max pooled in the forward pass. 1, 1, 5, 6, the max value is 6. 2, 4, 7, 8, the max value is 8. 3, 2, 1, 2, the max value is 3. 1, 0, 3, 4, max value is 4. So this in the forward propagation, for every 2 cross 2 region, you take the max element and put it here, and then you take it further through later layers. In the backprop step in the same layer, you keep track of what was the winning position in each 2 cross 2 window. For example, we know that 6 came from this position of the first 2 cross 2 window. So whatever gradient we have at 6 when we backpropagate goes to that location in the previous layer. Remember, backpropagation is drawn the other way here, but this is the previous layer. What you see on the right here is the previous layer. The full gradient at 6. Remember, we assume that when we backpropagate, the gradients until this step for each of these pixels is known to us. We only have to see how to backpropagate those gradients across the pooling layer. All this gradient goes to this location, all this gradient goes to this location, all this gradient goes to this location because that was the position of the winning neuron, and similarly for this to this. What happens if we did not use max pooling? If we used, say, average pooling? If we used average pooling, you would take whatever gradient came into one particular location, say the position of 6, distribute that gradient equally to each of these 4 locations in case of 2 cross 2 pooling. If you did 3 cross 3 pooling, you would divide that among 9 pixels. In this case, we have 2 cross 2 pooling. So whatever gradient you have at 6 will be divided into 4 and that gradient would be given to each of these pixels in the 2x2 neighborhood that led to 6. And that's how backpropagation is done across pooling layers. That concludes our discussion of backpropagation in CNNs. For more details, please read the lecture notes of Dhruv Batra on the same topic, or a very nice write-up by Jeff Keen on backpropagation in CNNs.